Hello, we are students from Cal Poly Pomona, and we are talking about our project for CSAF, Decoding Windows Events, making logs human readable with large language models. My name is Jake Ludlow.
My name is Nicholas Ramirez Ornelas.
I am Byron Wong.
And I'm Chris Avakian.
Jump right into our abstract. Our Windows Events logs generate gigabytes of cryptic log entries daily, which can be challenging for cybersecurity professionals to interpret. This project leverages the natural language processing capabilities of large language models, or LLMs, to translate these logs into clear, human-readable explanations. The goal is to enhance log accessibility for a wider range of users, including IT staff, security analysts, and non-technical users such as stakeholders. By bridging the gap between raw log data and understandable insights, this project aims to improve incident response, training, and overall system comprehension. Looking at our first figure, we can see the importance of choosing the right algorithm for these models. As you can see, there is a deceptively high F-score related to this algorithm, the SOFM DB scan. The outlier brings us to a very high F-score that is not representative of the average, which is somewhere around the middle, around 0.5. Moving into our objectives, the purpose of this project is to develop a solution that simplifies the interpretation of Windows event logs, enabling faster and more efficient responses to security incidents. These event logs are often delivered in a convoluted mess of words and numbers strung together to complete a single event. When investigating a security threat towards a system, there are often hundreds or even thousands of these events. It takes precious time to identify what these events mean, conclude on the current attack, and figure out the next steps to take to mitigate the attack. Our project aims to train an LLM to take in large amounts of log data and give back a simple yet detailed conclusion on the security event and risks at hand indicated by the numerous logs.
Moving on to figure 2, we can see a table very similar, a graph very similar to figure 1, but instead it's testing a different algorithm out. We can see, unlike figure 1, the F scores, there are not very many, there are no outliers in this one, so it's less deceptive. We're putting this figure in here to stress the importance of choosing a correct algorithm and testing it comprehensively. Moving on to our methodology. The process begins by collecting a data set of Windows event logs from publicly available sources to train the language model. A pre-trained large language model suited for log interpretation is then selected, followed by fine-tuning the model on specific log data to enhance its understanding of Windows event terminology and structure. The model's performance is evaluated using a combination of qualitative feedback from IT professionals and quantitative metrics like accuracy and log interpretation to ensure its effectiveness. In table 1, we can see five parameters being tested against large language models and some traditional models. The best of each column is bolded, and we can see while some are really good in certain columns, GPT-4 seems to be on overall to be the best option.
As for our results, deep learning models such as DeepLog and Log Anomaly have demonstrated promising results in log-based anomaly detection, achieving F1 scores around 0.95 on datasets like HDFS. However, these models are highly sensitive to data leakage, especially when random training data selection is used and their performance varies with different log grouping strategies and window sizes, making it challenging to capture anomalies across multiple sequences. Additionally, the imbalanced nature of anomaly data, where rare events occur in less than 1% of the logs, presents significant difficulties for detection. Issues like mislabeled logs and parsing errors further degrade the model's performance, which highlights the importance of data quality and proper pre-processing. Recent advancements with LLMs, such as Distill Roberta, have shown superior performance compared to the traditional models, opening new avenues for more robust and interpretable log analysis. These models offer practical benefits, including improved log interpretation accuracy, faster incident response by translating these logs more effectively, and increased user satisfaction as both IT professionals and non-technical users will find these logs more accessible and useful. While challenges remain in handling the data inconsistencies and evolving patterns, LLMs provide a promising direction for future research with opportunities to combine these with traditional methods for real-time log analysis and adaptive anomaly detection. And our figure 3 here shows it compares the performance of the log parser LLM with different LLMs based on the average number of LLM calls, the average time per interference, and the average metric space. And here, GPT 3.5 Pro and GPT 4 have low calls with a reasonable response time, which would indicate a good efficiency, while the fine-tuned Llama 2 requires much more calls to be just as effective. So overall, GPT 3.5 Turbo and 4 are more balanced, while Llama 2 requires more calls to achieve similar performance.
All right, so figure 4 is a TSNE visualization of the embeddings produced by the baseline and fine-tuned Distill Roberta model for all 6 datasets, with the left and right pairs representing application system logs. Each point on the cluster represents a log entry with red and blue corresponding to different logs. And the baseline model shows more intermixing of red and blue, indicating less distinction between the classes, while the fine-tuned model forms more distinct clusters, suggesting that the model has learned to differentiate log entries more effectively. And following the conclusion, this project highlights the potential of LLMs in bridging the gap between technical and non-technical users when it comes to system log interpretation. With the increasing complexity of security logs, the ability to translate them into plain language could significantly improve organizational incident reporting, alerting, and IT training processes. There are challenges to ensuring accuracy and consistency in translation, but the application of LLMs opens a new avenue for simplifying cybersecurity tasks. And following the conclusion, we have our references, and lastly, our acknowledgements. We would like to thank Professor Amamra and the California Polytechnic University, Pomona. Thank you.